in this example, I'll show you how useful current division is. So I'll restrict myself to using current division and maybe some simple resistor combinations to solve this circuit in here. So this circuit contains one current source in here that's a 20 milliamp current source and a bunch of resistors R1, R2, R3, and R2. And we're asked to compute a bunch of currents and voltages. So the currents that we're asked to compute is I1, I2, I3, and I4, and a couple of voltages, which is V1 and V2. The voltages are pretty straightforward because we know R, so if I know the I, I'll figure out what the V. The same goes in here. If I know the R in here, if I know I3, I'll figure out what V2 is. So it boils down to figure out the I's in here. Of course, I mean, your first intuition probably to use, well, let's use current division. Well, this 2 milliamp gets divided into here and here. And yes, that is true, but we can't use current division rule right away because as it turns out, this R2 is not connected in parallel to R1. Okay, R3 is not in parallel with R1. So what we need to do is we need to do a little bit of simplification because current division applies only to the case when the resistors are in parallel. So in order for me to use current division or I of S and I want to use current division, I need to combine these resistors together. And of course, after I do that, I probably will be able to solve most of the circuit. So let's see how we can combine these. And hopefully by now you would recognize that these two are in parallel, and we'll combine them with this particular resistor and become in series. So the result will become one resistor. We'll combine it with the R2 in series. So we'll get a resistor, and let's say the value of that resistor happened to be, I'm going to call it RA, for example. It will be simply R3 in parallel with the R4. And we'll add to it the R2. That's simply if we put the values, that's basically 4 in parallel with the 6 and plus 0.6. And we're dealing with kilo ohms all over. So I'm going to compute that. And we get 3 volts or 3 kilo ohms, sorry. So let me redraw that circuit with that 3 kilo ohm in here. So what I've done is I redrew that circuit here. So let's double check. The R1 stays the same. These resistors that are highlighted in blue become 3 kilo ohm in here. Okay, so let's double check what happens to the voltages and currents that I have. So what do I have? I have plus, minus in here. V1 stays the same. And I believe I1 stays the same. And if I actually, this is also I of 2, so I should be able to use I of 2 now, but with the RA resistors, not with R2, R3, and R4, because this particular current gets divided into I1 and this I2, but this I2, and actually now that I'm doing that analysis, you'll see that this I2 gets divided into I3 and I4 in here. So I should be able to apply current division initially to figure out what I1 and I2 is using this simplified circuit, and then we'll take the value of I2 and we'll divide it into I3 and I4 using current division as well. So it's straightforward to figure out the I1s and I2. So let me go through with this analysis. So what we need is the I1, and I know it's simply I of S times the other resistor, which is RA divided by R1 plus RA. Okay, and of course you can use the actual one, which tells me that it is the actual generic rule. Not only that applies to two resistors, you can tell me, well, it's simply I of S times R equivalent divided by R1, and you should be able to see that it is the same exact answer. You'll have to figure out what R equivalent is, which is the parallel between the 3 and 7. Anyway, so because it's 2, I know it. I memorize it because I've used it so many times. So I know that it's 2 times, or 2 resistors, that's what I mean. That's why I remember it, because it's 2 resistors in parallel. So that's 3 kilo ohms divided by 7 kilo ohms plus 3 kilo ohms. Okay, and that's basically 3 divided by 10. And the answer is 0.6 milliamps, because everything is in kilo ohms, so everything is and the source is in milliamps, so everything is milliamp here. All right, so we know what I1 is. Now what about I2? Well, you can apply current division again, or you can just apply KCL if you want to. It's the same. Well, 2 milliamp, 0.6, so it must be, the other one must be 1.4, but we can apply current division. So that tells me it's 2 times R1 divided by R1 plus RA, because the other resistor. So I'm interested in this, so I take the other resistor in here. So this simply is 2 times, I believe it should be 7 divided by 7 plus 3, which is simply 1.4. I was able to compute in my head 1.4. Okay, so we know that I of 2 is 1.4 milliamp. So here this is 1.4 milliamp, Well, I can use current division on this resistor here or in this circuit, and I can tell you, well, I2 gets divided into I3 and I4 because I3 and I4 or R3 and R4 are basically in parallel. We can apply that too. So we have the 4 and the 6. Okay, so let's do that. So that's simply I3 is simply I2, that's the source, and then I4 is I2 times, and then what are we multiplying with? If we wanted I3, we take the R4, okay? So if we wanted I3, let me just do that here. Okay, if we wanted the I3, we take the R4 divided by R3 plus R4. And if we wanted the I4, this one here, we take this resistor, which is R3. So this is R3 divided by R3 plus R4. You can do the calculation here, and you'll see that I of 2 happened to be 1.4. This is also 1.4 times R of 4. Let me just do that here. So R of R4 is 6 kilo ohms divided by 3 plus or 4 plus 6. And this one here is, I'm interested in R3, which is 4 kilo ohms divided by 4 plus 6. And we should be able to figure out what these numbers are. So this one happened to be 0.84 milliamp. And the other one happened to be 0.56 milliamp. And we can double check our result very quickly. If I sum up these two in here, which is 0.84 plus 0.56, I should get the 1.4, which I do, and you can sum them. So I4 and I3 gets added into I2 because it got divided into them. And of course, if you add I2 and I1, you should be able to get the 2 milliamp here.